So welcome back. I'm going to start with the question that was just asked in the chat. Maybe you can repeat it. Yes, I'm going to give you, I'm not sure if you have maybe the microphone of your laptop, but this also helps you be heard. So not in the same query, but in the same transaction, right? A transaction is made of multiple queries, and you could group these queries in the same transaction. The benefit that you get out of that is that it guarantees you that either the two will happen, the two updates, withdraw and credit, or none of them. None of them, that's also called a rollback. You might start modifying and executing your first query, and then you realize that for some reason there is an error with the second one, then you just roll back. You cancel and remove the effects of the first query as if nothing happened at all. Right? Does it answer your question?
Yes.
Yeah, awesome. All right, I have many more people on Zoom today compared to last week. So I told you last week that we had people collecting data from the stars. All the stars, all the galaxies, what we called nebulas before, and that's a lot of data. In fact, it's so much data, actually went and looked. Last time I checked, it was 273 terabytes of data. That doesn't fit on your laptop. 680,000 directories, 176 million files, doesn't fit on a laptop. So what do we do? How do we analyze that? Well, this is exactly why we have the big data lecture. And we are going to start with a place where to put that data. How do we deal with so much data? So we saw that we have those relational databases, but we already know that doesn't work because PostgreSQL is not going to be able to store so much data, right? So that doesn't work. So forget about it. PostgreSQL, over. However, we have a way of using new technologies, but still preserving many of the ideas and the constructs that we got from PostgreSQL and the like. So we have all of these years. I forgot to update the 48, it's even more now, but 99% of what we learn can be reused. Selection, we'll still have it. Projection, grouping, sorting, joining, we'll still have this in this lecture. Tables, rows, columns, primary keys will also still have it in this lecture. SQL will still have it. Declarative functional will still have it. Optimizations, query plans, that's the secret optimizations behind the scenes, will still have them. Indices to accelerate the queries will still have them. That's nice, right? We just need to swap the physical level. What we are going to throw away, I already gave you a warning of that, is the relational integrity, also called tabular, but relational integrity, domain integrity, and atomic integrity. We throw them away. The normal forms, we throw them away. We don't care anymore. And the data might be heterogeneous, might be nested, might be denormalized. I'll explain during the semester what all of that means. Nested, you already know, that's tables in tables, right? That's what we call NoSQL. In order to do that, to basically get this 99% of reuse, but swapping what we have behind the scenes, we are going to have to rebuild the entire technology stack. Stack, that's the name that computer scientists give to when you have multiple components in some architecture. It's called the stack. And so we are going to rebuild the stack that we had in a system like PostgreSQL, but bigger and better. So on the left, you have this monolithic relational database that would be PostgreSQL, fits on a single machine, right? And on the right is what we will have in this lecture that does the same thing, but in a data center on thousands of machines. So we go bottom up, right? We are starting today with the storage, where we look at S3 on Amazon and Azure Blob Storage. That's cloud storage as a service. Next week, we look at HDFS, which is another way. GFS, that's the Google ancestor of HDFS. You have your local file system, of course, on your laptop that can also be used to store data, just not petabytes. All right, so that's the bottom layer. That's where we store the data. Then we are going to have the encoding, but that we won't talk much about. It's just how do you encode when you have data that looks like text? How do you encode it to bits? Because you know that on the disk, it's all bits, right? So you have many ways of encoding it. Maybe if you remember one of them, just UTF-8. UTF-8 is just a way of encoding even international alphabets and international characters to bits. That's UTF-8 is what everybody should use these days, basically. Syntax, that's when we store data as text. For example, who heard of XML or JSON? YAML, yeah, many of you. So we'll study that in a couple of weeks. So CSV, maybe you also know, CSV is the tables stored as text. If you go to, I don't know, the Federal Office of Statistics or all these places to download data sets, you will see download as CSV, download as XML, download as JSON. So these are the formats in which you're getting your data from the internet when you download it. So we'll study this. We'll look into data models, the relational model for tables that we did in information systems for engineers, but we'll also look at trees in this lecture. Cubes, we also did in information systems for engineers. Graphs, we are not going to touch them. We shouldn't have too much material. So mostly we are going to focus on trees. The data models basically tell you how the data, once you have loaded it in your machine, is going to look like in memory and how you manipulate all of that with the query language. We'll spend 1 week of that. We'll validate data. Validating data means that after you downloaded a data set from the internet, you check for its integrity. You check that, for example, all of the values associated with a specific field are all integers or all dates, or that it has a specific structure. It's called validation. Validation is something you get for free in PostgreSQL because you're obligated to do that. But in big data, you're not obligated to do that. It's optional. So we'll spend also 1 week on that. Then we'll get to the meat of the lecture, my favorite part, which is the actual processing on the data. But that we can only do after we have built the model and so on, right? So we'll look at MapReduce, which is the first generation of parallelization systems in clusters, and Spark would be the second generation, which probably people know more Spark than MapReduce nowadays, but we'll again spend maybe even 2 weeks on this. I'll show you the internals, like how this is all implemented inside the data center to make the data flow around and output the right results. I'll tell you about indices. That will be all right. We're reaching the end of the semester now. So how to index data, just like what you have at the end of the books to make it faster. We'll look at data stores. So what we call a data store would be a full-fledged product that provides you with data storage and a way to process and manipulate the data, but without necessarily a language like SQL. So we don't call it a database system, we call it a data store, typically. So we look at MongoDB in particular. That would be an HBase, we'll also look at it. That's very large tables with millions of columns and billions of rows, to summarize. But that only in a couple of weeks. Querying, now this is getting serious now, where we have this high-level language that allows you in just a few lines in your Jupyter notebook to just query the data, right? So this is where the magic happens. SQL, you are brushing it up this week. We'll also use it in Spark. JSONic, I will give you a tutorial every week that it would be nice if you can learn a little bit every week. It's your predecessors who asked me to spread it a little bit over the semester, the learning of JSONic, to avoid that you just do it in a single week at the end of the semester. So we are going to spread it over the semester. And JSONic is a query language for trees. Just like SQL is a query language for tables. That's the way I would put it. MDX is a query language for cubes. And Sparkle is a query language for graphs, right? So you see you have query languages for all kinds of data shapes, right? So this is why I told you the shapes are important because they have an impact on the language you are going to use. REST API, I will talk about today. This is not a query language per se. It's more like, you remember that I told you application programming interface, right? It's this low-level way of accessing a system. But that I'll explain today, REST API. All right. And finally, we have user interfaces. That's when you use spreadsheet software. Who knows Tableau? Some of you, it's very used in the enterprise world. It's to visualize data and interact with some data and build dashboards. Now I should also add here now voice assistants and AIs and LLMs and so on, because this is getting reality, right? We can even put a level of, with a large language model and ChatGPT on top of this, which in the future should be able to query a database using SQL or this kind of languages and then give you the answer in English or in your mother tongue, right? So you see this whole stack from the very bottom where we store the data in the data centers all the way up to when it interacts with you via voice or via a screen, a computer screen with keyboard and mouse or microphone. All right. But we need to start somewhere because this is going to take us 14 weeks. So of course, we need to start small. So let's just do the storage today and start looking at this. So let's get back to the problem we have. We need to find a way to store the 273 terabytes of data. Well, it's going to sound stupid what I'm about to say, but it needs to be stored somewhere, right? So this is what physicists say. They say information is physical, right? You cannot have information without actually being stored somewhere. So we need to put it somewhere. There are two main ways of looking at the way we store data into a database system. One way is the PostgreSQL way. It means that the system takes over responsibility for everything. You just import the data at some point into the system, and then PostgreSQL deals with how it stores it on disk. You don't even need to look at the disk. It all takes care of it for you. It's all nicely hidden, right? So these are the traditional databases like PostgreSQL. MongoDB is the same. We'll see in a couple of weeks too. So here, you just need to import the data somehow. That's what we call also extract, transform, load, or ETL, which is a billion-dollar industry in consulting companies when companies need to transform their data and import it into their systems. And then on the other side, we have what is known as data lakes. You already heard of data lakes? Some of you, right? It's actually just as simple as saying we just drop the files somewhere and that's it, right? You download your JSON files from the internet, you download your CSV files, your XML files from the Federal Office of Statistics, and you just drop them on your hard drive. That's a data lake. Your hard drive is a data lake. We will see that we can also have data lakes in the cloud, right? Cloud storage, that's when you have, who has a cloud subscription, some online storage? Right? That's also a data lake, right? You just store your files. You can have probably pictures and videos, but also XML, JSON, CSV, so data that you put in there. And data lakes is what we are going to be doing today. We are going to study a system that allows you to store a lot of data, but in the cloud. Examples of usage of data lakes would be pandas. Whoever heard of or used pandas, such APIs? That's the data lake approach, because pandas is reading from the disk. You drop a CSV file or something on the disk, and then or writes to it, and then you manipulate it. Pandas is an API. It's an application programming interface. It's a Python library, as opposed to a query language like SQL. All right. We also call it in situ because you just query the data where it is. You just query the file and read the file where it is. By the way, you need to be aware that this is how it was done in the 60s before Edgar code, right? People used to actually do it the data lake way until the modern database systems appeared that took care of everything, right? And now with big data, something interesting happened because we took the step backwards and went back somehow to the way it was done in the 60s. I don't think it's forever. I think we will move back also for large quantities of data to the traditional system because it's much simpler to use and you don't need to worry about the details. But it takes a while, right? We're just seeing it in front of our own eyes that the technology is being designed. All right, so data lakes. So where can we store bits in the end physically? Well, on a disk, right? This is what it looks like. That's a mechanical disk. We also have flash storage, of course, like SSD nowadays, but it's going to be stored like this. This is what we can do. When we store the data on a disk like this, you know that it's stored in a hierarchy. You probably saw it on your laptop, not on your phones, but you have directories and files, right? What you may not know, but we teach it to computer science students, is that these files that you see, like it can be pictures, videos, Word, Excel, whatever files you have, JSON, XML. In fact, on the disk, they are stored as blocks. Blocks of roughly 4,000 characters, 4,000 bytes, right? 4 kilobytes. The reason is that it's much more convenient to read and write to and from the disk 4,000 bytes at a time, right? So this is why we have blocks. The reason has to do with latency. It's what I told you earlier about shipping a single zip file that you unzip on the other side. It's much faster to read 4,000 bytes in a single go, one after the other, than 1 byte at a time. Imagine that you read randomly some bytes from a drive like this that is mechanical, and every time you read a byte, you need to rotate the disk again and fetch the next byte to put it under the reading head, and that 4,000 times is going to take forever. But if you organize it in a block and you have your 4,000 bytes nicely organized on some line sequence on the disk, then you just rotate the disk and all the 4,000 bytes nicely line up under the reading head and are read in a single go, right? So this is why we have the blocks. It makes it much faster. And so we love to cut these files into blocks of 4,000 bytes and to read and write them in this way. Of course, you wouldn't know, right? Because your computer doesn't tell you that. When you open a file, it just opens it, right? You don't see the blocks. But hidden behind, it's actually done in blocks like this, right? And the file is just made up of all the blocks taken together. Okay. Who has some drive at their home that they use, they connect it to the internet and access it remotely? Any of you? Some of you, right? Very good. So this is one way of having some kind of cloud storage, but it's your own cloud, right? It's your own machine, your own drive that you have at home, right? You could also share it with other people, right? So that you could try to organize something like that. You could even connect several drives, right? And add the capacity of these drives. The problem is that it doesn't scale. What we call WAN is a wide area network, like ETH's network. All the Wi-Fi at the whole of ETH, that would be called WAN, right? A wide area network. Try to put the data on a disk, connect it at ETH, and tell the whole of ETH to access your disk. This is going to kill the disk. There is no way you can have thousands of people just accessing this one per disk at the same time. So we have a problem. We also have a problem in the quantity, because you might have thousands of files, you might have millions of files on your disk. Probably you see that when you do the backup. Who backs up their files? Who has a backup of their drive? If you don't have a backup of your drive, do it now. Do not wait until you experience the consequences. Really do it now. The International Backup Day is March 31st. So if you need a day to do it, then do it on March 31st, but back up your data. Then you will see the number of files when you do that, and it's typically thousands or millions. And billions, that doesn't work. You cannot have a billion files on your disk, right? So we have a scale-up problem here. We cannot go very far with that. However, we have some ideas that lie around on how to scale. And one example of idea was how to store electricity, how to store batteries. And one of the ideas that people had is that instead of trying to build a very big battery, why don't you take many small batteries and just put them together in some package and then use that to store the electricity? In fact, the word battery is supposed to be used when you do that. That's what you really should call battery, is when you assemble all of these little devices together. All right? And that we can actually do with disks and machines, and we are going to do it exactly in this way. Because these batteries are actually very cheap to produce. You just produce plenty of them, and then you assemble them. So what are we going to do? Well, we're going to get rid of the hierarchy for our storage system. We don't try to have any hierarchy. We just keep it flat. We just have plenty of files flat, right? They all have a name, but that's it. And that makes it trivial. The name is also called an ID, right? Identifier. We just identify every file, every picture, every video, every JSON or XML file. We give it a name, right? It's an ID. So we make it super simple. What we have is called the global key value model. The key is the name of the file, and the object, the value, is the file itself, right? So maybe you have here some data set you just downloaded. It's called dataset.xml. And here you have the actual XML, the file that actually could be very large, right? And here you have all of your files flat. There is no hierarchy in there. This is what we are going to do. And in order to get that scale, to make this, so this is a logical model, right? This is the idea that we have now. We can have billions or trillions of these key values, but now we need hardware to implement it. So if I take a machine and I want more space, the first idea could be to buy a bigger machine, or to add some memory, or to buy a larger disk, or a faster CPU, or more cores, and so on. The problem with that is that at some point it starts becoming expensive. Maybe you'll find a computer with 16 gigabytes of memory, 32 gigabytes, maybe 64 gigabytes of memory. 128 you can still do. A terabyte, if you put some money in it, you can do. A petabyte, so a terabyte you can do. A petabyte, you will not find that. You could try to then build it, but you're going to have to spend probably billions of dollars in order to do it because it doesn't exist. So you see that this approach doesn't scale, right? It only brings you so far within what is commercially available, and the prices do not go up linearly. So there is a trick, and that trick is the same trick that I told you about with the batteries. Instead of trying to buy a bigger machine, we just buy another machine, and another machine, and another machine, and plenty of machines like this, thousands of machines like this, right? This is called scaling out, as opposed to scaling up. So this is scaling up, this is scaling down. This is scaling out, this is scaling in, right? When you remove machines, scaling out, scaling in. All right, and this approach scales linearly because every computer costs the same price. So you just need to, if you want the total price, it's the number of computers times the price of a machine. Of course, it always has its limits because if you want 1 trillion machines, then probably you're going to hit the limits of the economy. But at the scale of a company, it actually works, right? So the marginal cost of a new machine is more or less constant. This is what we call scaling out. And here I put a very simplified view, but basically the idea of scaling up is that it grows up exponentially and even hits a wall, because past a certain limit, you will not even find any commercially available machine that is big enough. But scaling out, as long as you don't reach the scale of the entire planet, it's still going to be linear, right, in cost per bytes. So this is why we love to scale out. But I have a third way that I'm going to tell you about after the break. So I'm keeping that cliffhanger. See you at 18 past 9 for the continuation. Thank you.